Hello class. Topic 2 introduces us to ordinary differential equations, or ODEs. Let me go back to the first page. Here we go. Page 1 of our guided notes. An ordinary differential equation, or ODE, is an equation involving at least one derivative of any order, so I mean first, second, third, fourth derivative, etc., of a function of a single variable. Now, there are also functions of multiple variables, which you learned in Calculus 3, and there exist partial differential equations, or PDEs. Now, this class will only focus on ODEs and not PDEs. Resuming the reading here, the solution of an ODE is a function that satisfies the ODE and meets any other specified criteria. A solution can be a general solution, meaning a representation of a family of functions, or a particular solution, meaning a unique function. Find the solutions for each ODE below. Okay, so what makes this an ODE? I see that there is an equation, and it involves a derivative, a first derivative. We are assuming that this is a derivative with respect to a single variable. So this is y is a function with respect to a single variable. Notice that there are two variables involved in this equation, x's and y's. And because the derivative is located on the y, we are going to assume the following. We're going to assume that x is the independent variable. So it's the input variable of the function. And the y is the dependent variable. Furthermore, this y prime that you're seeing here is specifically, it's a lazy way of saying y prime of x. So y is a function of x. Or you can use Leibniz notation and say dy dx. Often I'll be lazy and just put a single prime next to the variable that's the independent, or the dependent variable, and we'll assume that the other variables involved in the equation are the independent, in this case the x's. So our solution is going to be of the form y of x. We're trying to find a function that satisfies this statement. Well, this is going to be as simple as doing an antiderivative. So the original function, y of x, or just y, is, let's do an antiderivative rule on 4x. We increase the power from x to the 1 to x squared and divide by 2. And there's already a 4 there, so we just get 2x squared. And just quickly verify, the derivative of 2x squared is that 4x. And then we need to do an antiderivative of negative sine of x. That's going to be positive cosine of x. And don't forget, we need this plus c, meaning that any function of this form, where c is a constant, will be a solution to this differential equation, to this ordinary differential equation, or ODE. It's easy to verify that this is, in fact, a solution. All you have to do is find the derivative of this, plug it in for y prime, and see if you get the same thing as that. In other words, we just have to show that the derivative of 2x squared plus cosine of x plus c is, in fact, 4x minus sine x, which it is. This is called a general solution, and we say it's general because c could be any constant. There were no other stipulations that told me what c has to be, because we're trying to satisfy this differential equation, and this family of functions satisfies it for any constant c. Now the other case. Over here we have a different ODE with an extra condition on the solution. Also, we have different variables. We have z's and t's. Notice the derivative is in Leibniz notation, so you could write that instead as z prime instead of dz dt is equal to 4t minus sine t. Notice that I cross my z's. I recommend you do the same when they show up. Otherwise, they look like 2's. Now you'll notice that this is the exact same differential equation as this one, but with different letters is all. That's the only difference. So again, to find z, to find the original function, z of t, z is the dependent variable here, t is the independent variable, and we do an antiderivative. We get the same antiderivative as we got before, but with t's instead of x's. Yep. And then we have plus the constant. So here's our general solution. to the differential equation, but we have enough information to find a particular solution next. We want it so that z of 0 will be 3. So we plug in 3 for z at the same time I plug in 0 for the independent variable, in this case t. So we get 3 is equal to 2 times 0, 0, that's gone. Cosine of 0 is 1 plus c, so that tells us that c must be 2. And now I'm able to write down my solution as a function of t. It's going to be 2t squared plus cosine of t plus the choice of c that we just determined. And this is a particular solution. Let's write that down. Particular solution, as defined right here. Particular solution. Now these are very simple ordinary differential equations that all you had to do is just do a regular antiderivative of the independent variable to get the original function. Now there are multiple types of differential equations, of ODEs. One way to differentiate from one to the next, or distinguish one from the next, is what the highest derivative present is. So a first order ODE involves the derivative of a function of one variable but no higher, meaning just the first derivative but no second or third derivatives or etc. are present. So here's an example of such a thing. I see two variables here. We have y's and t's. The prime is on the y, so the y is the dependent variable and the t is the independent variable. And notice the highest derivative present is y prime. The rest of this can be anything you want. There could be y's, t's, there can even be another y prime. This could also be a y prime over here, and then there could be a plus 8y, and then you could divide everything by t. There's so many, as long as there's just two variables, t's and y's, and only the y's have primes on them. And this would be an example of a first order ordinary differential equation. So let's give another example. I'm going to use u's as my dependent variable and x as my independent variable. You can write any equation you want involving u's and x's. So this would be an equation involving x's and u's, but it's not a differential equation because there's no derivative involved. So to get a derivative involved here, maybe if I put a prime on that u, or maybe put a prime on that u, or put them on both u's. But if you put the prime there, then all of a sudden we've created a first order ordinary differential equation. A second order differential equation involves the second derivative, but no higher. So here we're using Leibniz notation. If I were to write this without Leibniz notation for these derivatives here, remember this is a first derivative here and that's a second derivative there. So this one might have been written this way instead. 3x plus 2z prime is equal to 4 minus z double prime. And since there are two variables present, only one of them is allowed to have primes on it, the z in this case. So z is the dependent variable, and the other variable, the x, is the independent variable. You didn't have to have a z prime present either. Like this, that could have just been a z, and this would still be a second order differential equation because we have a second derivative, but not higher, involved. Okay, let's do another example of one. W will be our dependent variable, and let's go back to t for our independent variable. Usually we'll just deal with x's and t's as independent, and then a variety of letters as the dependent. So just making stuff up, e to the w plus 6t to the third is equal to w minus 5wt. Just any equation you want to come up with that has w's and t's. And then w's are the only things that are allowed to have derivatives involved. And to be a second order, we got to get a second derivative. So let's make this w here be the second derivative and this w here be a first derivative. And we'll leave that w as just regular w. So we've just created a second order differential equation in terms of w and t. And then, of course, higher order differential equations involve at least the third derivative. So here's one involving w. Notice I don't see a second variable here. There's another letter. So we can just assume that the independent variable is whatever we want. We can say it's x, we can say it's t. Usually we'll use x or t for independent. But the differential equation doesn't have to have both letters. So as a second example, let's do z is back to our dependent variable, and x is back to our independent variable. So only z's can have derivatives, but we could have z's. We don't have to have any x's at all. We could have z, third derivative of z times 5 minus 6 times z second derivative plus 8 times the first derivative minus the original function is equal to 0. And here I've created a differential equation that has no x's involved, which is fine. X is the independent variable. It has only z's and its derivatives, and the highest derivative present is z cubed, or z to the third. Not z to the third, I shouldn't say it that way. The third derivative of z triple prime. Okay, next definition. An ordinary differential equation is linear if it can be written in the following way. And I've done it for first, second, third order, and then you can generalize to higher order if you want. So notice I have the highest derivative isolated, and I'm using y as the dependent and x as the independent in these examples. Highest derivative is isolated, and then on the other side, we just have a coefficient times y plus a function over here. But the coefficient of y has to be a function of only x, and the function over here has to involve only x. So in other words, we just have y prime and at most y. If you put a square on this y, then it's no longer considered linear. So in other words, the derivative has to be raised to the first, and all the lower than the derivative, so in this case only the function, has to be raised to the first. And then they can be combined using any coefficient involving the independent variable, and then having a independent variable function over here. This is called a linear first order differential equation, ordinary differential equation. A second order one will have the y double prime isolated, and on the other side we have a y prime raised to the first, a y raised to the first, and then we have coefficients. It could be any functions of x, doesn't matter, and then you could have a coefficient of x or a function of x over here off on the side. So this would no longer be linear if I put a square root on that y. Why not? Because that would mean a 1/2 power, and a 1/2 power is not a 1 power. Right, so it has to be this form in order to be linear. Y prime to the first, y to the first. Nor could you have a y prime times a y, because this is a term that is like a second degree term, if you will, because it's a function times a derivative of a function. It's kind of like having a function to the order of 2. It has to be very specific that you have to be able to write it in this form, where the y prime is isolated with a potential coefficient involving maybe x or maybe just a constant. That could be a 5 that I have circled, or it could be a 5x. So be constant or have an x. And then the y has to be isolated with a coefficient that involves constants and or x's, but that's it. And then we have a function over here, or maybe no function. Maybe some of these are 0 as well. Like that, this function here could be 0, meaning that this whole term right here isn't visible. Right? So you don't need to have all of these terms here, because this could be the 0 function, that could be the 0 function, or that could be the 0 function as an option. And then a third order linear differential equation has the third derivative isolated, and then the first derivative and non-derivative, the 0th derivative, if you will, are all alone on the other side of the equation with potential coefficients. It could be 0, it could be constant, some other constant, or it could involve x. These coefficients could be very complicated. This thing I just circled, the b of x, could be 6x cubed minus e to the x plus sine of x all over the arctangent of x, right? Just as long as there's only x's and or constants. Same here. This could be constants. It could be 0. If that's 0, then this would not be visible. And again, that also can be any function of x, including 0 or constants. And you would have a third degree linear differential equation. What would make this not linear is if I multiplied this y double prime by y prime. Then we have a second order term right there. We don't want that for linear differential equations. If I divide this by y squared, then we have the y has to be isolated right here with a possible coefficient. There can't be y's elsewhere throughout this. That would not be linear. It would still be a differential equation, just not a linear one. I couldn't put a third power on that y. That would not be a linear term as far as y or its derivatives are concerned. So the only freedom you really have to tweak these and still be linear is to tweak the coefficients. All the things I'm circling here, those you can let them be whatever you want, including 0, constants, or expressions involving x. But the rest of the structure has to be pretty much exactly as you see it. Okay, now let's do some examples. Let's determine the order of each ODE, identify the dependent and independent variables, put the ODE in normal form, which means to isolate the highest order derivative, kind of like what you see is happening here, and then determine whether the ODE is linear. Okay, let's start with, we can do these in any order here. Let's start with the order this is. Highest derivative I see is a second derivative right there. So this is a second order differential equation. And the independent variable, well, the derivative is on y, so the only other variable is t, so that t is the independent variable, and the dependent variable is the y, whichever one has the derivative. This would not be a good differential equation if there was a t prime as well. You can't have derivatives on both of the variables. It's going to be on only one of the two variables, and that's the dependent variable. Put this in normal form. We haven't done that part yet, so let's just solve this for y double prime. So if you add t and divide everything by 2, so I think I can do that all in one step. Add t and then divide by 2. So we have 3/2 t times y, add t and divide by 2, plus t/2. Okay, notice the structure. Notice how it mimics this structure right here, except we're using t instead of x as the independent variable. So we have y, oh sorry, I circled the wrong one. How it mimics this structure. So you have y double prime isolated, check. Notice that we don't have this term present. That's just simply because we can let a of x be 0. So these terms don't all three of these don't have to be present. So that one there is not. We do have a something times a y. So the coefficient here is the b of t. That's this 3/2 of t is the b of t that's in front of the function y. And then plus some arbitrary function of t, so we have plus this t/2. All right, so if you were really wanted to get to what this general structure looks like, you would say it's 0 y primes plus, and then we have a function of t, I'm calling this the b of t times y, and then plus a function of t at the end. And you can see we have this structure here, specifically where the a function is 0. Okay, so because it can be put into this form, we do have a linear differential equation. Okay, the next one. The first thing that jumps out to me is the order. This is I only see a z prime, so this is a first degree ordinary differential equation. We haven't determined if it's linear yet. The independent variable, well, the prime is on the z, so the only other variable is x, so that's got to be the independent variable. The dependent variable is the z, because it has the derivative. Solve for that derivative. So I'm going to add z sine x to the other side of the equation and then divide everything by z. So we get z prime is equal to, and hopefully this isn't too much work that we're doing in our head, we have 4x divided by z and we've added z sine x to the other side, but then divided by z, so we should just have plus sine of x. Okay, so we put it in normal form. The z prime is isolated. The question is, does it look like this general structure? So we have z's instead of y's, and we have x's, or the x's are the same. But I can definitely see there's the f of x right there. But notice that if I were to bring this z in the denominator up, it'd be z prime is equal to 4x times z to the minus 1 plus sine of x. So we could say that this is the a of x right there, and this is the f of x, but this is a z to the minus 1. It has to be a z to the first in order to be a linear term. Right, all the powers on the dependent variables and their derivatives must be power 1. Right, this is y prime to the first. That's y to the first. Y double prime to the first. Y prime to the first. Y to the first, etc. Right? All the dependent variables and their derivatives must have powers 1 when they're brought up. Like it'd be a mistake to look down here and say, oh, that z has a 1 power on it, therefore this is a linear equation. That's not the case, but you can't be dividing by the variable z. You have to put it into a linear structure and then look at that power and see, oh, that's a z to the minus 1. This is nonlinear. All right, let's do this last one. The thing that jumps out to me right here is that w triple prime. So we have a third derivative involved here. So this is a order 3. The independent variable is going to be the t then, and the dependent variable will be the w's. We can solve this for w triple prime, get the highest ordered isolated. See if I can do this in my head as well. I'm thinking of adding this to that side, subtracting that to the other side, and then dividing everything by e to the t. So it looks like in the end we have 2t over e to the t times w, and then minus radical t over e to the t w double prime. Hopefully I didn't do too many steps. Feel free to do this in multiple steps. Take your time, make sure you get this right. I'm just looking at it right now to make sure everything looks good. Okay, it does. Now typically though, if you want to write it in the correct order as indicated above, that you would put this w double prime term first and then plus there. Okay, so now we're trying to mimic this structure that I see for a third degree. I have the dependent variable to the third derivative of it isolated, check. I've got the second derivative of the dependent variable present, so that's there. So that tells me that the a of t, not a of x, but a of t is this function that involves only t, check. I don't have a w prime involved, so b of t must be 0, that's gone. And I have a c of x times y, so that's our c of t right there, times our dependent variable w. And then I don't have an f of t present, so that's 0 as well. But this does fit the linear structure, because w and all of its derivatives are all raised to the first, not being multiplied by each other or anything like that. All right, next slide. Use your knowledge of functions and their derivatives to solve each ODE with initial condition below. All right, so if this had been y prime equals x, this would not have been challenging, because we would have simply said, oh, then therefore y is 1/2 of x squared plus c, and then I would have found out what c was using this initial condition, just like we did on our very first slide. But it's not y prime equals x, it's y prime equals y. So then some might think, oh, then do this. Just do the antiderivative of y and get 1/2 y squared plus c. But look at this, is a weird statement. This is not a solution, because we're trying to get y as a function of x as our solution. That doesn't work. We're going to need, if over on this right side of the equation there's nothing but x's or t's or whatever the independent variable is, then we just need to do regular antiderivatives of that side and we get an answer. But we have a y present. So this is a little bit more complicated of a differential equation. What I'm trying to find is a function y such that when you differentiate it, you get the same thing. Right? Isn't that exactly what this is communicating to us? We're looking for some function y such that y prime is the same as y. So reach into your derivative formulas and try to think of, hey, what's a function whose derivative is itself? And hopefully what comes to mind is the e to the x function. And notice there is no independent variable mentioned here, so we can assume it's x, we can assume it's t, we can let the independent variable be whatever. It hasn't been specified by the equation, or dictated or implied by the equation. So it seems like y of x, if it's equal to e to the x, then it will be true that y prime will be equal to y. The question though, is this the only solution? And some might say, oh, put a plus e then, that'll do it. But let's test this if this works. If you do the derivative of this answer, we just get e to the x, right? Because the plus c would go away. And then I would plug this would go in for the y prime right there, right? Or just this part there would go in for the, so we trying to recreate this equation is equal to y. Is it true that e to the x is equal to e to the x plus c for any c? Well, the answer is that's not true. It's only true if c is 0. It's not true for all c. So a general solution to this, it's not e to the x plus c. But if you think about it, if you were to put a constant in front of e to the x, would this be okay? Because what's the derivative of a constant times e to the x? Let's check this, see if it works. Y prime of x is equal to, well, this constant would stay and the derivative of e to the x is itself. So yeah, this one does work. If there's an arbitrary constant in front of e to the x, then we have a solution, a general solution to this differential equation. Y prime will be equal to y. So here's our general solution. I'm going to put GS next to that for general solution. Now let's find the particular solution using this initial condition. So we know that, oh, I should say this is our general solution. And I'm going to just use this line here to verify that, to show that we verified that our general solution works. Okay, so this line right here is simply showing that our general solution here satisfies the differential equation. Check. Y prime is equal to y. Okay, now let's go for the particular solution. I'll put general solution like that. Particular solution. So we know that y coordinate will be 3 when the x coordinate is 0. So we write this down, and we got to figure out what c is. Well, e to the 0 is 1, so therefore c must be 3. So I can rewrite my general solution. Y is a function of x. Or if you want to be lazy, you can just say y is equal to the constant 3 times e to the x. And this is our particular solution. And we got it by simply just because there was a simple function in my toolbox, if you will, whose derivative was itself. And I was able to generalize that. Okay, let's do the next one. Double w prime equals 2w. Okay, so now there's a 2 here. Let's see if we can start guessing. Well, again, w is the dependent variable, and I don't see an independent variable indicated. Let's just go with x again. So we're trying to figure out a w function of x, such that when you differentiate it, you get twice what you started with. Again, if this was an x, not a w, then this would be an easy problem to do, but it's a w. So we're trying to find a w function such that when you differentiate it, when you do w prime, you get twice what you started with. Well, if you remember the chain rule, right, if you were to find the derivative with respect to x of like e to the 5x, do you remember what happens here? Don't you get itself, but then you have to multiply by the derivative of the exponent. Ooh, that's interesting. So the derivative of e to the 5x is itself, but times 5. Well, I'm trying to find a function whose derivative is itself, but times 2. Right, you see where I'm going with this? If I let the function be e to the 2x, then it will be the case that w prime is equal to e to the 2x times the derivative of 2x, which is 2, And that's the same thing as 2 times the original. So check, that works. But this is already specific. There should be a general solution of this. And again, if we have any constant here in front, let me rewrite this part here, that constant will stay when you do the derivative. So we're still going to get twice the original. So there's our general solution right here, some constant times e to the 2x. By the way, I'm a bit pulling these solutions out of the hat, relying on just my understanding of the derivatives I'm already familiar with and trying to make this phenomenon happen. We will later in this course talk about how to start with this and then systematically come up with this solution. But that's to come later. And now we want a particular solution, so I'm going to take my general solution, right, change this part here to minus 5, change w coordinate to minus 5. At the same time, I change the x to 0, because that's what's indicated there by the independent variable. And so we just get negative 5 must be equal to c. And so I get a particular solution of the following. W is equal to, and I could write w of x, but I'll just say w, is equal to c, which is minus 5, times e to the 2x. And this is our particular solution. I'm going to go ahead and circle these. So that's what we're after in these problems. Now, I leave it to you to verify that both of these statements are satisfied. If you take the derivative of this expression, you will get twice that expression. And the other thing to verify is if you plug 0 into this function right here, if you plug 0 into that for x is right there, then you will get negative 5 back for w. Okay, now let's look at the q's. Again, I don't see any second variable here, so let's just assume x is the independent variable. And q of 1 is equal to negative 2, q prime is equal to negative q squared. All right, so this one's tricky. Can you think of a function that when you differentiate it, you get the opposite sign, but the square of it? And if you want, you can pause the video here and then wrestle with this a little bit. I promise you that it's a simple function that this happens. And then when you're tried it on your own, you can replay the video and see what I do. Well, it turns out that the function we're after is 1 over x. Let's just verify that. That's the same thing as x to the minus 1. And if you differentiate x to the minus 1, you get negative x to the minus 2. Well, that's just negative 1 over x squared. Wasn't that can't you write that as negative 1 over x squared? In other words, it's equal to negative q squared, because q was 1 over x. Right? Think about that. Seems like that's working. So if I differentiate this function q, I get the negative of the square of q. So it happens with a very simple function, 1 over x. And let me delete that for a moment. This is still a particular solution. I want a general solution. If I put a plus c over here, then it won't work out because, because when you differentiate, you're just going to get negative 1 over x squared, which is not equal to negative q squared, because q has this plus c involved. So we're going to get around this issue by putting a coefficient in front of this 1 over c instead to make it general. This should work. Constant over x. Let's check it. Q prime is equal to negative constant over x squared, which is the same thing as negative... Ooh, this isn't working either, is it? Because we get... Ooh, this one is not going to work, because if I try to take the square out, I get a radical c over x squared. This is not equal to negative q squared. Okay, so we got to figure out a different way to generalize this one. And right now I'm just sort of guessing and checking until I figure it out. We will eventually learn how to solve this explicitly and get the answer really quickly. But right now, let's see if we can figure this out. What if I do 1 over x and put the constant, add it to the x down there? Let's just see what happens with this. Right, this is the same thing as x plus c, all raised to the minus 1. So if I differentiate that, I get minus, and then x plus c raised to the minus 2. which is negative, let me write it down here, 1 over x plus c squared, which is negative 1 over x plus c, all of that squared, which is negative q squared. So this does it. Able to find the general function such that q prime will be negative q squared. Okay, so we have it. This is our general solution right here. Now let's find the particular. We want q to be negative 2 at the same time that x is 1. So I get this statement. Right, I'm just taking the general solution, changing q to negative 2 at the same time I change x to 1. I'll just go ahead and delete that and write this up here. There's our general solution. And then solve for c. So I'm going to multiply by 1 plus c, so we get negative 2 minus 2c is equal to 1. I'm going to add the 2c, subtract the 1, so minus 3 is equal to 2c, and then divide by 2, so negative 3 halves is equal to c. So our particular solution is going to be q is equal to 1 over x plus c, which you could write as, if you want to double top and bottom, if you don't want like that fraction in there. Either of these will be fine for your particular solution. Now I do leave it to you to check it. Do the derivative, see if you get the opposite of the original squared, and then plug in 1, see if you get negative 2 out of this. All right, let's do a little bit more guess and check with some differential equations, but this time second order, and we won't go to third order, not in today's lecture. That's down the road. Use your knowledge of functions and their derivatives to solve each ODE with initial conditions below. Okay, so now we want a function whose second derivative is equal to the original. All right, so we have a second derivative is equal to the original. Well, that's certainly true for e to the x, right? So if we were to say y of x is equal to e to the x, the second derivative would be the original. And to make it general, I could put a constant here. But we want y of 0 to be negative 5. Okay, let's plug in 0 for x. And I do leave it to you to verify that if you do the second derivative of this, it's the same thing as the original. So the second derivative is equal to the original. And plug in 0 for x at the same time y is negative 5. This tells me that c must be negative 5. So we get a solution that is y is equal to negative 5 e to the x. This will work. Turns out there's another solution though. I'll just reveal it. Or see if you can pause the video and see if you can think of it. There's a second solution to this. A second function that I can think of when you differentiate it, you will get the original. There's actually a few options here. Here's the second one. Try it. Do the first derivative of c e to the negative x. First derivative would be negative c e to the negative x, right, using the chain rule. And then the second derivative, another negative would multiply going back to c to the negative x. So we get back to the original. Okay, so there's another one. Of course, I'm not asking you to find all of them. I just asked you to find one. So we found one. But c e to the negative x or negative 5 e to the negative x would also work. How about this one? This one also works. Oops, the cinch. Because y prime takes you to cosh, and y double prime takes you back to cinch, which is what we started with. Right, so cinch is another solution. And then you could do any constant in there as well. That would make it general if you put a constant there in front. Another one is cosh, right? Because the second derivative will be back to cosh. So y double prime will equal y. But cosh and cinch are also combinations of e to the x and e to the negative x. So they're really just sort of versions of the other solutions we've already talked about, c e to the x and c e to the negative x. leave that to you to ponder for a little bit. What about regular trig? What if I said y was just sine of x? Would that one work? Let's see. Y prime would be cosine of x, and y double prime would be equal to negative sine of x. Well, this is not the original. It's the opposite of the original. So sine of x would be a good solution to y double prime equals negative y, not y double prime equals y. So regular trig isn't cutting it here. But hyperbolic trig did work, as did e to the x and as did e to the negative x. These are things to think about. When you have second order differential equations, you can get multiple answers, multiple functions, multiple very different functions, right? Not just multiple because of the different choices of c that could be made. We'll talk more about that as we explore the second unit of this course. I should also mention at this point that we're doing an introduction to differential equations right now, but the unit 1 primarily, focuses only on first order differential equations. Unit 2 will be second and higher order. And there's only 3 units in this semester. Okay, next one. We have x. Oh, this time x has got a derivative on it, which means it should be thought of as the dependent variable, which requires a bit of a change in our thinking. We're so used to seeing x as the independent variable, but now we're treating it as the dependent variable, which means we need a letter for whatever the 0 there is, and that's probably going to be, let's use t. So we have x of t is our function here. And we're trying to find a function whose second derivative will be negative 9 times the original. Well, that negative showing up makes me think regular trig. Let's see if we can get the 9 to work out right. So if x was equal to, and we need a variable here. Independent variable. It's not implied because I don't see any other letters. So let's just go with the t. Let's test x of t equals cosine of t. So the first derivative would be negative sine t, and the second derivative would be negative cosine of t, which is equal to negative of the original. So we're really close, except we don't have the 9. So how do we get a 9 to show up after 2 derivatives? Well, think chain rule. If this was a 3t, then the first derivative would be negative 3 sine 3t, right? Using the chain rule. Let's get rid of those parentheses. You don't really need to write them. And the next derivative, chain rule again would happen, so another 3 would multiply to this, getting negative 9 cosine 3t. And this is, in fact, negative 9 times the original. Check. So I found a function such that when I differentiate it twice, I get negative 9 times that function. But now we want to make this general. And to make it general, again, we'll put a constant here in front. If you don't like c times cosine, too many c's, you can put an a in front if you want that as your constant. So you don't have cc, it looks kind of funny. But when you put an a in front, then the only thing that's going to affect is that there's going to be an a still there. And then here, there's still going to be an a. So we still get negative 9 times the original. So it still works. And we have a general expression. Now to get a particular solution, change this part here to 3. At the same time, you change t to 0. Well, 3 times 0 is just 0. That's not, I don't mean to write 30. That looks bad. Let's put a 0 there. Cosine of 0 is 1, so the a is 3. And so we get, in the end, our particular solution is x is equal to a, which is 3, times cosine of 3t. And I leave it to you to verify that this will satisfy this differential equation, and will also give you 3 when you plug in 0. Another solution to this one would have been sine. Let's just test that real fast. If x is equal to a sine 3t, then x prime will be 3a cosine 3t, and x double prime will be 9a, then a negative sine 3t, right? Because the derivative of cosine is negative sine, which is the negative 9 times the original function, right? Which is just x. So that also works. And then if you solve for a, you actually will get 0 in this case. A would have to be 0 because if you plug in 0 for t, ooh, this is interesting. Maybe this one isn't a solution, because if you plug in 0 for t, sine of 0, 0, so we just get an impossibility. So actually it looks like this one is not, this one satisfies the condition here, that x double prime is equal to negative 9x, but it's not possible to use this general function to satisfy this condition. Right, so something there to think about. So it seems like so far we seem to have only found one answer here. But our goal isn't to find all the answers. That's for a later topic. We just had to find one. I'm just trying to illustrate that when you have second order differential equations, multiple answers become something to think about and try to find. And this last one, v double prime equals 5v. That looks a lot like this one over here, except there's a 5 in front. So I'm thinking along the same lines. V of, let's go back to x, v of x is equal to some constant times e to the, and I want the second derivative to produce a 5. So if I put a 5x here, then the first derivative will produce that 5 that I want, which is equal to 5v's. But I want the second derivative to equal 5v's, not the first derivative. So I need the 5, because if I do a second derivative, that will produce a 25 in front. Right? Which makes me think, oh, well, 5 is probably not the good coefficient. How about radical 5? Let's see what happens here. V prime is equal to radical 5 times c e to the radical 5x. And v double prime, which is where I want to go, another radical 5 multiplies to the other radical 5 in the front, getting just a 5 c e to the rad 5x. This is 5 times the original. Check. And v of 0 is equal to 1. So plug in 1 for v at the same time you plug in 0 for x. So radical 5 times 0 is just 0. So we get c is equal to 1. And so our particular solution is v is equal to 1 times e to the rad 5x. And there's our particular solution. I leave it to you to verify that the second derivative will be equal to 5 times the original, and that when you plug in 0 for x, you get 1 back for v. Both conditions satisfied. Okay, so what we saw in these last two slides was a lot of guessing and checking, using our knowledge about derivatives to find solutions to these differential equations, both first order and second order, to realize that second order has multiple answers that were acceptable. I only left visible one answer for each of these cases, but multiple answers becomes something to think about with second order and higher order. And we will later in this course learn how to solve these same kinds of problems, but more directly, not with this guessing and checking approach. Okay, a few more slides to talk about here. What does it mean to suggest that population is changing at a rate that is proportional to its population size? Okay, population is changing at a rate, so we need to have some variables involved. If population is a function of time, right, at different moments in time, there can only be one population of like a country or something else, or population of a petri dish, and you're counting bacteria as your population or something like that. So population is a function of time. So I use P for population, T for time. Population is changing at a rate, right? So that suggests a derivative. So this is saying that P prime of T, this is the rate at which population is changing with respect to time, is changing at a rate that is proportional to its population size. To be proportional, if you might remember from modeling in an algebra class, when I say A is proportional to B, sometimes this symbol is used, A is proportional to B. This means that A is equal to some constant times B. This happens all the time in everyday life. For example, the amount of money you spend on burritos is proportional to the number of burritos you buy. So, and K would be the price. So you put in the number of burritos times the price and you get how much you spend, right? I mean, just a very common type of situation, price, speed, and, you know, the if you're traveling at a constant speed, how far you go is proportional to how long you've been driving. But when two things are said to be proportional to each other, that means they are equal, that one is equal to some constant times the other. That's what I'm trying to say. So the rate at which population is changing is p prime, is proportional, so it's equal to some constant times the thing that it's proportional to, its population size. Well, that's just the function p of t again. P stands for population. So population is changing at a rate that is proportional to its size. That means the bigger the population, the faster the rate of growth. Now this should make sense because the more people, let's presume we're talking about people, the more people out there, the higher their reproductive rates, because there's more people to reproduce. So you gain more people per year when there are more people. And if we're going with a model that the rate at which population is changing is proportional to the population size, that dictates this mathematical sentence. And let's go ahead and specify that this stands for the population at time t. That's the function. We can leave off the of t's if you want. If you want to rewrite this equation more simply, it would just be p prime equals kp. And we just created a differential equation. The textbook likes to use Leibniz notation, so you'll see this often. And the nice thing about Leibniz notation is that when you write only this, it's not clear which letter I should use as the independent variable, so I feel free to use whatever ones I want. If you see it written this way, then it's pretty clear that t is the independent variable. But if it's written this way, it's also clear that t is the independent variable because of that dt down there. But let's go ahead and go with this most simple way to write this differential equation. P prime equals kp. That looks a lot like something we did right there. W prime equals 2w, except I'm using p instead of w, and k for the constant instead of a known 2. So now we're going to give a general solution to the differential equation above. P prime is equal to kp. We want a function that when you differentiate it, you'll get k times the original. Well, borrowing from what we did up there, that population, that p of t should be, and we're looking for just a general solution, not a particular, should be any constant, let's go with a for the constant, times e to the kt. And let's just verify real fast, right? If you take the derivative of this, the a will stay, the chain rule will pop out a k, and e to the kt, and that k, of course, can be written in front of the a, right? So you can write it this way. And this part that's in parentheses is just the original function again, so you get kp. So we have found it. Here is a general solution for our population growth. And you might notice it's an exponential curve. So when you graph it, you expect to see what you would expect to see in a population that had no growth inhibitors, just exponential growth. Okay, last slide. We're going to create one more model based off a sentence. Suppose a population is growing at a rate that is proportional to the product of its current size and the difference between its current size and a maximum capacity of a population of 1,000. Okay, there's lots of things to think about here. So we have a population growing at a rate. So again, we have a p prime is proportional to the product. So is proportional is equal to some constant times, and then some sort of product is going to happen here. Is proportional to a product. Now, what's in the product? What are the two factors? Well, the product of its current size, well, that's just p, so that's one of the factors. The p stands for the population size. And the other part of the product is specified right here. The difference between its size, so that's the difference between p and a maximum capacity of a population of 1,000. So we're assuming the population is below the maximum capacity. And if the max capacity is 1,000 and population p is below that, then their difference would be 1,000 minus p, as opposed to the other way around, because then we don't want this model to suggest that we are over the max already. Let's assume that we're not over the max, that a population is under the max and still growing. So this is the differential equation that results. Let's just make sure that this makes sense reading it. So suppose a population is growing at a rate, so that's p prime, that is proportional to, so it's equal to k times something. And what is it proportional to? A product, so k times a product of its current size, which is p, and the other factor is the difference between its current size and 1,000. And there's the other factor. This probably has one set of parentheses too many. That's not necessary, but here's a good concise way to write this particular differential equation. K is a constant, and p is the dependent variable, and t is the independent variable. Okay, that wraps up our introduction to ordinary differential equations and their solutions and how to do some modeling.